move on now to our final presentation of the day, and that comes from Amatec Land. James, are you ready to take the podium?
Yes, thank you, Matthew. Thanks to Christian and to Will for that great presentation. I'm zooming in a little bit. We're going to talk about heaters, process gas heaters and steam methane reformers. This is it's quite a nice area for me. I've spent the last 5 years in the Middle East looking at all types of process gas heaters in the petrochemical industry. But my background was traditionally in the steel and heat treatment industry. 15 years really on furnaces of all types, in furnaces of all types. So very happy to present today a little bit of a focus on some of the temperature technology that Amatec Land provides. Many of you probably know Amatec Land for pyrometers, especially on rolling mills, in steel plants, for liquid metal temperature measurements, lag detection in the primary steelmaking process. And it's really nice to talk about DRI because of that synergy to our petrochemical business. So quick recap. I know you've seen this in previous presentations, but in gas-based DRI, iron oxides reduced in the presence of reducing gases that I'll come on to. Coal-based DRI, I'm not really talking about that today, but rotary kiln and hearth furnaces mix lump ore and coal. We do have actually a lot of installations on rotary hearth and rotary kiln furnaces, generally for calcination processes in the cement and lime industry, and also in India in particular in the DRI production world. But really we're talking about this natural gas route, and that's either through process gas heaters or steam methane reformers if you do have a reformer on the DRI plant. So just zooming in on SMRs for a second. So SMRs in DRI production, in my experience, and this is over the last say 3 or 4 years where we've started to look at DRI, you've typically got a bottom fired reformer in the case of Midrex, or you've got a terrace wall fired reformer in the case of a Foster Wheeler design that's used in other DRI processes. So the majority of syngas production around the world comes from natural gas, which comes from the steam methane reforming process. In DRI, obviously there's a process gas heater route where gases are just heated, not reformed, not cracked before entering the shaft furnace. Or as Will and Christian mentioned, you could have a reformer where you've got this large number of tubes, large number of burners, a lot of things really that you want to know the temperature of, and that's where we come into the picture. So just a quick recap on the process gas heater route. So that's where you wouldn't have an external reformer. You've just got a process gas heater, oxygen addition before that goes into the shaft furnace. This is obviously not in the Midrex process, but you've got, in this case, a terrace wall reformer supplying mixed syngas or mixed hydrogen and CO into, again, process gas heater. So there's still a process gas heater after the reformer, before the reactor. So in this case, we can supply our technology to both the terrace wall reformer and the process gas heater. In the case of the Midrex process, where you've got a bottom fired, typically pretty large reformer, when you compare these steam methane reformers to the ones that we might be familiar with in the refinery hydrogen world, the ammonia world, the methanol world, the CO2 production world. You know, these are big reformers, and it's really critical given the elevated temperatures that we get the temperature monitoring right. So just recapping, how is thermal imaging used? I just wanted to recap on some of the advances in thermal imaging in the last few years. So on DRI plants, and this is true across actually specific plants in the US, we've really supplied across the range. So you might have a thermal imaging camera looking at flares, monitoring the pilot status or the main flare status. You might have thermal imagers looking at assets, so monitoring the outside surface of furnaces. That may be in the steelmaking plant as well, on ladles, gasifiers, anything where you're concerned about the refractory degradation or steel surface temperatures. CMTs that I'll come on to in detail. And then obviously the material itself, if you're concerned about the combustible material during storage or during transportation, then you can also use thermal imaging and infrared technology to monitor that. So thinking about accuracy for a second. So why is accuracy when measuring tube temperatures important? So either a steam methane reformer or a process gas heater, relatively simple equipment, really, just very hot tubes, processing gas or reforming gas, and we're measuring the surface temperature of the tubes, and the accuracy is important. Accuracy is important there because we operate in this specific window. If you're inaccurately high, so if your real temperature is 900, but we're telling you it's 950, then you'll have methane slip. So that means the methane that you're trying to break down, you're trying to reform, is going to go into the header, and you're going to measure that in the gas analysis. You're also going to have a margin loss. This is typically if you're an over-the-fence supplier. So if you're supplying syngas from outside the plant, you might have a margin loss, so you're producing less products than you need to. Or you're chasing false alarms, so you think you've got a problem. I say this is probably the most common challenge that we run into. Your operators or your technicians, your inspection teams are chasing ghosts, really. They think they've got these high temperatures, but they don't actually have those. Inaccurately low is probably more dangerous. That's where you might have safety issues, problems with reliability of the equipment, so tubes going really over their temperature because they're much hotter than you believe they are. You'll have margin loss there by reliability, and you'll also really significantly affect the tube life. So just a small over temperature, small period of over exposure to higher temperatures can take off 10 years of life in the case of your 20-30 degrees C over your design temperatures. So a couple of small case studies. One of our customers, Beck, who supplies services in the US to all types of fired heaters, actually identified around about 12 times return on investment on their service. So using infrared equipment to identify fired heater over temperature issues, they identified about this 12 times return on investment. Using data from ammonia know-how that we work with in the ammonia industry on primary syngas reformers, they identified that around 22% of equipment failures cause shutdowns, and they involve the primary syngas reformer. More than 50% of those failures involve tube wall temperature excursions. So that's either during startup or during operation. A tube wall temperature excursion was responsible for shutting the plant down. So what we've worked on with all the hydrogen producers, syngas producers, is increasing that production while still operating in a safe window. So just a couple of the failure mechanisms that you might experience, you might be familiar with from steam methane reformers. You might have your carbon formation on the inside of the tubes. That's where your mixture of catalyst and mixed steam and natural gas. You might have that caused by a low steam to carbon ratio, so your process gas is too rich. You might have heavy hydrocarbons in the feedstock. The catalyst activity could drop, so that means the inside tube wall and process gas temperatures increases. Carbon formation rate exceeds the gasification rate, so you get formation on the inside of the tube wall and on the catalyst. You could have loaded the catalyst incorrectly. You could have fractured the catalyst, or it could be settled in specific voids. Insufficient purging of the residual hydrocarbons prior to restarting the furnace, or you could have intermittent or complete loss of steam. So that type of carbon formation in a steam methane reformer is, and on other types of heater actually, is normally visible in a thermal image through this type of hot band, and that's usually visibly apparent as well. And then once you have that carbon formation, the reduced inside, you get a reduced inside tube wall heat transfer coefficient. You get reduced interpellet heat transfer coefficient, so less heat being transferred between the catalyst itself. Lower catalyst activity as the active nickel sites are covered in carbon. And then you get a pressure drop, you get an increase in the resistance to flow through the affected tube, decreases the heat sink available, and then further increases the tube wall temperature. So you can have this kind of runaway effect whereby your tubes start to overheat. When one tube overheats, it radiates onto other tubes, so you can get a kind of knock-on effect where you've got multiple overheated tubes. What we typically see is producers reduce firing around those tubes, but to increase the general level of firing, you can increase firing in other areas, so you get a reduced overall efficiency. And then to remove that carbon, if you need to, producers reduce those temperatures, steam decoke tubes, and then you obviously get carbon gasification, producing significant volumes of CO2 in that case. So reducing severity of coking hot bands can have a pretty significant impact on your general efficiency. So what we do in this industry is supply a range of instruments, starting with the very basic. This is a handheld pyrometer. This is something that an operator typically walks around the plant with, takes notes either on a piece of paper or on a tablet or a laptop, records those values. They take these values typically without any correction factors, and then they'll go into the office after to correct those values. We also pioneered a product called the Gold Cup. So on a steam methane reformer or process gas heater, if you're measuring using a non-contact method, there's a few variables that can cause errors. That might be the emissivity of the tube itself. It might be the background temperature causing errors, so you get background reflections off the tube onto your pyrometer from the tunnels, from the sidewalls, from the roof, from other hot tubes, and you can also have interference of CO2 or water vapor in the atmosphere. So what we do is we actually hold this very long water-cooled probe against the tube surface to give ourselves a reference method. So this is a reference temperature that we can use to calibrate our thermal imagers or our pyrometers. So your pyrometer is going to give you a single tube measurement, but you can obviously measure all the tubes that you can see, and your Gold Cup is going to give you a reference measurement that you can use to calibrate that imager. What we've talked a lot about in this space is thermal imaging. So what a thermal imager enables you to do on a large process gas heater or steam methane reformer is to measure multiple tubes with a single imager through a peak door or through a custom port. So that's kind of automating the tube metal temperature measurement process. And we can do that with certified imagers on the left, 3.9 micron imagers in the middle, or high definition imagers that you can see on the right. The high definition imager is particularly attractive to this space because unlike some of the petrochemical producers, we're finding that DRI producers are happier to go with non-certified equipment, and that's based on probably some of the experience in the steel industry. But really, we don't really need to have certified equipment around a firebox that's running at 1050 degrees C. So we've designed a range of housings for this imager. The key thing really to note is that the electronics are in this housing here, but the actual lens is on a borescope. So that means that we can get the lens really in the furnace. We can cool that borescope and still get the benefit of a really wide angle view inside the furnace. So we can do that on a fixed basis. We can cool that with water or with air, or we can do that on a portable basis where you've got a borescope with a kit essentially that enables you to carry that round the reformer, open your peak door, take your measurement, record those video files on the tablet, and then go back to the office to review those video files. So that gives you some kind of versatility with the imager. Some of the things that we found is particularly useful in this space. You can see if you're measuring upper levels, you can often see cold air ingress. You can really see the uniformity of the tubes around the furnace, and then create thermal maps of the reformer to give yourself an understanding of the balance of the reformer. And you can do that on a periodic basis with that tool. You can also see the temperature gradient of multiple tubes vertically, so we can see how the reaction is happening in that tube. So I've got some images of a running Midrex reformer, and thank you to Will for the kind permission to use these. So this is actually using this portable system with a view to demonstrating the value of a fixed system. So we took the imager through the peep doors. The images, as you'll see, show some pretty interesting stuff. So this is just basically showing that we used the very small peep hole on the Midrex reformer to put this borescope through. Second image shows you how we determine the tube temperature. So we actually put these regions of interest at 3 levels. So you've got a region of interest on your top level, your middle level, and your bottom level. What this is doing is collecting essentially a line of information across the length of the firebox, and we can actually use that data, like you can see here, to show that the temperature uniformity of those tubes as you go towards the center of the furnace is actually quite good for such a large reformer. In some of the industries we've worked in, some of the sites that I saw in the very hot regions in particular, they would struggle to get this type of uniformity. So just with a kind of 2-minute analysis, you can really see and you can monitor for peaks, for troughs, for elevated temperatures, just with a really simple analysis. What we can also is look at the tube seals. So again, very quick analysis, but you can see here, this is the minimum temperature measured in that region of interest. So I can determine again with a quick analysis that there's no real major problems on the tube seals or with the tube seals. That would be very obvious, and if there were a problem with the tube seal or with cold air ingress around the tubes, you'd see temperatures way below 1020. You'd see something like 600 or below. So we're able to make those determinations. What we can do by highlighting certain temperature ranges, so this is highlighting about 1050 to 1120 degrees C. We can really see how the tubes are balanced. We can see high contrast across the tubes, and we can see really even things on the floor. We can see how the radiance is affected across the length of the firebox and how that might be affecting tube temperatures. But again, in this case, kind of unfortunately for the presentation, everything in the reformer is running well and nicely balanced. So there's no major issues to report from this one. So that on a fixed basis, so if we were to fix a camera in a reformer, and this is an example from an ethylene cracker in Europe, that's how a camera would look fixed. So that's actually with an air-cooled system at number 1. Number 2 is just a bracing plate and a welded standpipe to the furnace case. Number 3 is the cooling jacket, and then number 4 is just your power and communications cables. So we've determined the angle of that installation based on a field of view analysis and a consultation with the customer to determine what the optimum placement of those cameras might be. Again, these reformers are very large, so if you were to fit an entire firebox with cameras, it's probably a pretty big number of cameras in order to automate this TMT and furnace monitoring process. So it's generally a consultation where we say, well, there's a requirement for say up to 6 or 8 or 10 or 12 cameras, and now let's determine the real best place to put this to get the most value from that. So that's the type of process we might do. We might decide to look at the bottom of the tubes. In the case of a terraced wall reformer, we might be looking at the bottom because that's where we think the hottest temperatures might be. On the case of a mid-rex reformer, we might be looking further up the process, given that's a bottom fire process. And we've developed a ton of software features, not just to collect the information, but to correct that information. So we can correct that for emissivity, for background, using real live data. And then we also monitor for the temperatures of both the camera and the tip of the camera during installation. So we try to make sure we're monitoring not just the furnace, but the health of the camera itself. And then that's just an example on a large steam methane reformer in Qatar, where we actually, and this is just a sample image, on a long-term basis monitored every single one of these tubes in this image with only 2 cameras. So with the camera on the opposite side, you could actually measure, I think it's 36 tubes on each row. And then the camera from the opposite side will measure the first 36 tubes on each row from the opposite side. Again, coming back to the definition quickly, just the last couple of slides, you've got a real advantage in terms of pixel resolution when it comes to high definition imaging. So this is the same image, but with 3 million pixels versus 300,000 pixels. And this gives you a good idea of how target sizes and pixel resolution is important in thermal imaging. With a smaller pixel size, we're actually able to detect higher temperatures. So if you were to determine this tube temperature, the temperature of this hotspot, with a lower resolution imager, you might actually miss that it's actually up at around 950 degrees C, not down at this 920 degrees C. So that's why in thermal imaging, target sizing and spatial resolution is a pretty important concept. The same with monitoring the burner temperatures. We get a difference of about 40 degrees just based on the definition. Isolating certain temperatures, we can also see the direction of the flame, or at least the flame impingement or flicker on that back wall. And we can see that that does have an impact on the tubes themselves, as the tubes on the right-hand side are hotter than the tubes on the left-hand side. And then obviously long-term, and something we currently do is build this into real-time dashboards to give our users an idea of the real-time tube temperatures, the alarm situation, the trends over time, comparison of rows to each other, and then this thermal gradient to give you an idea of the real temperatures. And then looking at efficiency, by increasing efficiency, we can lower oxygen concentrations to optimize the combustion, reduce fuel consumption safely, monitor for loss of flame. On process efficiency, if we're balancing tube wall temperatures, we can increase the feed efficiency, lower methane slip. We can monitor for increases in tube temperatures, and that impacts the heat transfer coefficient and steam to carbon ratio. And then we can do all sorts of things for safety as well. I've run over slightly, so I'll finish there for questions. And again, just thank everybody for listening and the great presentations previous to now.
Thank you very much, James. Yeah, quick question. Can these cameras be used to view the burden temperature inside the furnace of a DRI plant?
Just repeat that, sorry, Matthew. Can it be used for?
Yeah, sorry. Can these cameras be used to view the burden temperature inside the furnace of a DRI plant?
The burner temperature, I guess, is the question. Depending what you mean by burner temperature, and obviously we have a lot of applications where we are actually trying to measure flame temperature. We're actually designing this system to penetrate flame, so we're trying to see through the products of combustion. So we're actually trying to measure metal and refractory temperatures. We're not really trying to measure flame temperature, but with the right camera in the right application, we have measured flame temperatures. If the question is more related to the shaft furnace itself, that's something we haven't actually put a camera on the inside of yet, but would be very keen to if we were given the opportunity to.
Furnace. Hello?
Yep, sorry.
Sorry, there was a slight glitch then. How long can the camera survive in a sort of high temperature furnace?
The, the actual environment it's in is, I just compare it to a normal office environment. The camera actually lives in a normal office environment. It's cooled to the temperature of the cooling medium. So whether that's water or air, as long as the temperature is below about 45 degrees C, the camera will survive for 10 years without a problem. We do have cameras that we install. We first started installing these in about 2012 and 13, and we've got cameras still running well since then. So the actual environment the camera itself is in is very comfortable. The environment of the cooling jacket, not so much, not so comfortable, but we designed that for glass melt tanks that run at about 1800 degrees C. So the cooling jacket itself stays pretty cool in these comparatively lower temperature processes.
Okay, there's one more question from, if I can work this. Helen asks James, she might have missed the information. Can you restate what is the camera resolution? Like, what is the temperature resolution the camera can detect?
Yeah, so camera resolution on the high definition is 1980 by 1020. I could be wrong. I'll share this presentation. So that's the pixel resolution. So say 3 million pixels. So each one of those pixels will give you an accuracy of about 0.5% of the measurement. So on a 1000 degrees C tube, we can give you about an accuracy of plus or minus 5 degrees C. Sensitivity is about a degree, so it will detect changes of plus or minus 1 degree C. I always compare the kind of temperature measurement on these heaters to measuring your weight. You don't really care what your exact weight is. There's no academic reason to understand your exact weight, but you like to know if you're getting too heavy or otherwise. So what we're really interested in with imaging is not absolute academic accurate temperatures. We're really interested in measuring changes, rate of change, and then if we're getting over those critical temperatures.
Okay, well, look, James, thanks. Thanks for a great presentation. Before we go, actually, there are quite a few questions on the whole hydrogen DRI thing that a lot of people have written in. I know we had a little glitch with the sound or the actual availability of the question box. So I was going to ask a few more questions to, well, let's put it open. Let's say to Rutger, Will, and Christian, and James, if you want to come in. Just a couple more questions. One from Vaman Shanbag, which is, in the future, would H2 based DRI be a better option over molten oxide electrolysis technology to produce greener steel? I don't know. Does anyone want to answer that question?
I can if you want.
Okay. Far away.
Let's try it. I will try to answer it. Again, first of all, in German we have the saying, there are many ways to Rome. I'm very sure that the DLR of the H2 based DRI would, I guess, round about 9 to 10, where the molten oxide electrolysis slices is in 2 to 3. So they still have a long way to go until they really come up with a working industrial plant. Because to have something in laboratory or in small scale doesn't really mean it's possible to do it in the big scale. And to my knowledge, it's not. There are some upscaling issues which needs to be solved first before really going ahead.
Okay, thank you for that. I've got one now, I think, for Will, which is from Jennifer Wise, and she says, blast furnace pellets typically don't have the same metallurgical properties as DR pellets and are typically smaller. Does this have any impact on the Midrex process?
Yeah, so your reduction would still be similar to a DR grade pellet. With that, more of that gang in the pellet. Christian kind of hit on it. You're gonna have to deal with it downstream. It's not like we can get rid of more gang in our process. What goes in is gonna come out. So process wise, it's not gonna change much. We still typically like this pellet size in the range of 9 to 16 millimeter. But with that gang, you sometimes can create more fines. So there's a little bit of productivity concerns. But like we said, there's a few commercial DRI plants running blast furnace grade pellets now and not having real issues. So we don't expect it to change much. And their pellets are a little more abrasive as well, the blast furnace grade. So a little more wear and tear, but process wise, the reduction would basically still be the same.
Okay, thank you very much.
Could I join in for a second?
Feel free to drop in there.
Yeah, because I just like to, when we talk about new processes, you mentioned the molten oxide electrolysis, and I started my career in the 80s, and we then had a large amount of new processes coming on stream to replace the blast furnace, because we had an investment situation where companies didn't feel that they could afford new agglomeration plants like coking plants and pellet plants, etc. And there were really many promising processes. And what happened was that very few of them survived. Some have become niche processes, but most of them have actually disappeared for several reasons. Very often about productivity, very often about maintenance issues, because you underestimate the difficulties that you have with molten iron oxide, which is very aggressive. As I see it now, I think that talking about the niche the new processes coming on stream, I think that the most important is actually the smelter, and Christian mentioned it, and I apologize for not mentioning it, because it is really important and may replace the blast furnace as an extra melter. It will, however, take some time before it's really a key, and where you can see it in a large scale and changing the iron making landscape. But must remember this: new processes are good, but we have such an enormous amount of money and time put into the existing processes that if we want something to happen fast, we should try to see how we can use the existing processes, the existing raw materials, to decrease the CO2 emissions, if that is what we are after. Thank you.
Okay, actually, I have a question really, because I've just written an article that's going to appear in the May-June issue. It's the second article I've written on this subject, and that is the electric smelter. Now, I did an exclusive interview with Gerald Wimmer at Primetals Technologies. Previously, I'd interviewed somebody at Danieli Chorus. There's a lot of chat now around the electric smelter and the fact that it can use low-grade iron ore, whereas the EAF tends to be looking at higher-grade ores. What's the view of the panel on the potential for the electric smelter?
Being Primetals, of course, I see a big potential. Again, for me, at the moment, it's still the only alternative at the moment we have, because the smelter is actually a direct reduction plus smelter is actually a blast furnace, with the big difference. In the direct reduction, we just have the direct reduction, like in the upper shaft of the blast furnace. And in the lower furnace, where we have the coal in the blast furnace, we are now using the electricity. And out of the need that we have to find something for these low-grade iron ores from Australia, I mentioned already several times, this is the only way at the moment, I think, that we really can use these iron ores. You can, of course, try to beneficiate, but also beneficiation has its limits, especially on the economical side. So we need also, beside the mechanical beneficiation, we need also some kind of thermal beneficiation. This, of course, is for me at the moment. The only one we just see in the picture is the smelter.
Hey, Rutger, do you have a view on the electric smelter?
Yeah, it's an interesting process, but we must remember that we had electrical smelters until quite recently, and what happened with the electric smelters was that they were used for ferroalloy production, for example, but for pig iron production they were not. They were suffering from refractory wear and productivity. So these are issues that has to be solved, and I'm quite sure that Primetals will solve that. But it is still a development that has to be done, and also we have to deal, if we're working with the electrodes, we have to actually get non-fossil electrodes. So it is a challenge, as we used to say, and it will be solved, but it will take some time, I think.
Okay. Well, look, we've sort of come to the end of the process. I think we're just on hitting 2 hours now, so it's been quite a long webinar, which is great. As I said earlier, the Future Steel Forum this year takes place at the Hilton in Stockholm, 17th to the 19th of June. There will be a discussion panel on DRI, along with other discussion panels on AI, and indeed the whole question of, how do we define green steel? So if you want to go to Stockholm in the middle of the summer, next month basically, then do go on to the website www.futuresteelforum.com. Check out the program. Rutger will be speaking, so will Primetals Technologies. All the big steel makers are there, especially SSAB Hybrid, H2 Green Steel. It's going to be probably one of the best conferences we've produced. So hopefully I'll see you all there. I'll certainly be seeing Rutger there. And everybody enjoy your weekends. And next time we run one of these, I'll see you all again. Thank you very much.